Hi everyone, we are from Gokraju Rangaraju Institute of Engineering and Technology. We have done a project on strength characteristics of soil stabilized embankment using FLYASH. I would like to give a brief description about this project in the coming slides. Coming to the introduction, infrastructure projects such as highways, railways, water reservoirs, all linked to the civil engineering projects requires earth material in very large quantity. And quite often we encounter soils that are highly plastic and also highly expansive, which are not suitable for the purpose of stabilizing any project. So for this purpose, we need to stabilize the existing soil embankment. This may be done in many methods, and our present focus is stabilizing the soil using the FLYASH. Generally, soil stabilization refers to the process of changing soil properties to improve strength and durability. There are many techniques for this stabilization process, and two of them are mechanical stabilization and chemical stabilization. Mechanical stabilization includes compaction, ramming, etc., whereas chemical stabilization includes adding lime, cement, fly ash, geotextiles and geogrids. This figure shows you a photo view of our black cotton soil that is used in our project. This gives you the microscopic view of the FLYASH that is used in our project. Coming to the tests that are to be conducted on the soil, sieve analysis, liquid limit, plastic limit and standard compaction are to be conducted on the soil to know the properties of the soil. Sieve analysis. As we all know, this test is performed to determine the percentage of different grain sizes that are contained within the soil. This figure gives you a set of sieve sizes that are to be used in the laboratory. Starting from the 4.75 mm sieve, it goes till 0.075 mm. This tabular form gives you the results that are obtained in the laboratory for the soil that is considered. Our ultimate aim is to find the percentage fines that are written on each sieve. Coming to the Atterberg limits, one of the Atterberg limits, liquid limit. Actually, the liquid limit is the water content at which a soil changes from a plastic consistency to a liquid consistency. For this, we use Cassagrande liquid limit apparatus, and this figure gives you a view of liquid limit apparatus. These are the results that are obtained for the liquid limit of the considered soil sample. This graph gives us a detail of the water content that is to be added to the soil sample. The other Atterberg limit, that is plastic limit, as we all know, this is the minimum water content at which a soil will just begin to crumble when it is rolled into a thread of approximately 3 mm in diameter. This gives the process of the sample preparation for the plastic limit test. These are the results that are obtained for the plastic limit test. The optimum content of the water that we got is 53%. Coming to the compaction. Compaction is the process of increasing the bulk density of a soil or aggregate by driving out air. It is an essential test to determine the optimum water content and also the maximum dry density. This land diagram gives you a brief description and also an overview of the compaction apparatus. This is the sample preparation in the laboratory that is to be carried out in the compaction test. After compacting it, the excess soil is to be trimmed for leveling to the top of the mold. The figure on the right shows you the process of the sample extraction that is to be carried out after the compaction is done. This table gives you results that are obtained from the compaction test. Water content for the various cages of the loads and also the bulk density is 2.137 and also the dry density is 1.96 for various loads that are imposed onto the soil. This chart gives us an overview of the compaction test from which the OMC and MDD can be determined. Coming to the California bearing ratio, Actually, CBR value is an index for the shearing resistance of the soil, and it is the heart of this project. CBR actually indicates the load bearing capacity of the soil. So we need to find out the CBR for the soil sample considered. If the value of the CBR at 2.5 mm penetration is greater than that of the 5 mm penetration, the former is adopted. This table gives you the results that are obtained for the normal soil sample, and the CBR values are indicated as below. The CBR value for the normal soil sample at 2.5 mm penetration obtained is 5.5%. Later, we added 5% fly ash to the soil sample, and we found the CBR value for 2.5 mm penetration to be 7.61%. From this, we observed a slight increase in the value of the CBR from the normal soil sample to that of the soil sample with 5% fly ash. Later, when we added 10% fly ash to the soil sample, we found out the CBR value for 2.5 mm penetration to be 6.597, slightly declined to that of CBR plus 5% fly ash. And even for the CBR soil sample plus 20% fly ash, we found out the CBR value to be decreasing to 6.09%, from which we can infer that the CBR value for the soil sample is maximum with the addition of 5% fly ash to the soil. We also need to find out the so-called CBR values for the soil sample. This is done to find out the load bearing capacity of the soil in case it encounters any expansive soil, and the value is found out to be 1.24 for 2.5 mm penetration. This table gives you the results that are obtained for the so-called CBR values plus 5% fly ash, and the value is found out to be 2.92% for 2.5 mm penetration. This figure shows you the soil samples. The first on the left is soil plus 10% fly ash, and on the right is soil plus 20% fly ash, and below is soil plus 10% fly ash. And the ultimate results that we obtained are CBR for the plain soil sample is 5.5, CBR for the fly ash and soil mixture of 5% fly ash is 7.61, and on the further addition of 10% fly ash, it reduced it to 6.597, and even on the further addition, it decreased it to 6.092. From the following graph, we can infer that the CBR of the plain soil sample increased with the addition of the 5% fly ash, and then gradually declined with the further addition of the fly ash. So from this, we infer that the optimum content of the fly ash that is to be added to the soil sample is 5%. Unconfined compression strength. The basic idea behind this test is we are dealing with the soil embankment, so that way we need to have C5 values, since the soil embankment will have some changing slopes. So to determine the C5 values for the soil sample, we need to first know the UCC, that is the shear strength, and also the compressive strength of the soil, which are determined from the UCC test. This figure shows you a brief view of the UCC apparatus. This table shows us the results for the UCC soil sample, that is a normal soil sample, and the ultimate shear strength and the compressive strength that are obtained. This tabular form gives us the results for the normal soil sample and also the 5% fly ash, for which the compressive strength and also the shear strength are found out. Finally, I would like to conclude this project in a manner to increase the stability of the soil embankment. We need to initially find out the value of the CBR, which is actually the required element in finding the stability of the soil. So in any case we encounter any expansive soils, instead of replacing the soil, we're actually stabilizing the soil, stabilizing the existing soil by addition of fly ash. This way our project becomes more economical, as well as the stability values of the subgrade can be increased. Thank you.